right. Hello. Thank you for waiting. Today's meeting is going to be an extension to PWN. We're going to be talking about some more primitives and attacks you can do on more complicated binaries, and generally talking about like the larger expansive program space. This is not focused.
You get that.
Okay. Announcements. We have a workshop with Cesar Creek this Friday, so please come. They want people there, and we want to bring people there. And there will be free pizza. All right, meeting flag. I have provided a valid format string for you to type into the meeting flag. I'm sorry. All those are technically allowed. And there was also a tweet about someone who named their Wi-Fi invalid format string, and now they bricked their iPhone. But this was a while ago. I'm sure it's patched. I hope. Yeah, just name your router to like %n, %p. I don't know. Pat it 500 times. Okay. So let's review PWN I. We talked about how buffers can be allocated on the stack. They're usually at like a fixed size and space. And they're all contiguous in memory. So if I define like 2 integers in a row, the memory for the second integer will be before or after the first integer. We explained some unsafe functions that will take an input and just write it into that buffer location with no concerns to the bounds of that buffer. And so this causes a buffer overflow vulnerability. With that, you can overwrite the return address and control the program flow and make binary do something unexpected. So today, I want to briefly touch on shellcode. This is kind of the next step into controlling a program's flow, in the sense that if there isn't like a win function in like your prototypical CTF challenge, you can write your own. So shellcode is just bytes that we plan to execute. And so there are many types of shellcode to do many different things. There's just an example of assembly here. We have the assembly meeting from a few weeks ago to tell you how to write this stuff. And the one I've linked here will pop a shell. It'll run bin/sh on the host machine when ran. And so we can do whatever we want, but we can write this onto our stack, for example, and attempt to return to it. So if we have a stack variable and we know the address of the stack, we can overwrite the return address to be a location on the stack where we then placed our shellcode. And so, our shellcode may be 20, 40, 80 bytes. And so if we move the return address to point to the stack, it will just start going down the stack and using it and, setting up our function calls and doing something malicious. So that's shellcode, but it is easily mitigated. The largest mitigation that's kind of provided on all binaries as standard is NX, or non-executable stack. And so the way you run shellcode is you need to be able to write your shellcode into a location and then jump to it to execute it. Normally, executable sections of your code is only read and execute only. So with this, there's a philosophy of how to manage memory regions, is that you never give any memory region both write and execute permissions. You don't want programs writing their own code while they're running. Back in the day, this was not considered. It was only added to the Linux kernel in 2004, which is 20-something years ago. But besides the point, binaries before that, this wasn't like a major protection included. So a lot of the challenges we give you will have this off. But as you get to more and more real binaries, you can expect that the stack will never be executable because it's just a whole host of issues. And so now with like bigger like issues that come up with how we mitigate exploitations with buffer overflows, there are ways to deal with that. And the first one introduced, I think, in like 2006, was stack canaries. So what this was is that at the start of a function call, the processor would generate a random number and place it onto the stack right after the return address. So it would push the return address and then place this random number. And what would happen is when you call return, you never actually write this function out. This is inserted by the compiler. What would happen is before every return statement, it would then check the value on the stack with that random value that's stored in a register that's never touched. It would check whether those don't equal each other. If they don't, then we crash the program. We don't even there's no safe handling with this. It just crashes. It assumes something has gone horribly wrong, and we don't want to let the user to cause any issues with our program. So this was another mitigation introduced, and it makes buffer overflowing quite hard because if you don't know what's on the stack, then if you try to overwrite your return address, you're just going to crash instead. And finally, we have something that confounds our situation even more, and this is two protections that work hand in hand called ASLR and PI. ASLR stands for address space layout randomization, and PI stands for position independent executable. So normally, like before, with these protections disabled, our code is loaded into a fixed address, and it expects that fixed address when it's doing jumps and calls and things like that. And normally I think it's set to like OX40, like 400000. But if we turn pi on, that means all of our jumps, calls, so on are all relative. They don't expect anything about the initial address. So this allows us to take advantage of ASLR, which is provided by the kernel. ASLR says, hey, I'm going to randomize all the positions of where your executable code is, where libc is, where the heap is, where the stack is, so that a new user can't expect anything about what's going on with the program. They need to know, they need to have like some exact address to figure out where a specific region of memory is. And just because you have one address of a region does not mean you have all of them, which makes this hard to kind of like travel throughout your program space during execution. And so if pi is enabled for your binary, that means that it's no longer a fixed address, and it's usually placed around like 55, and like the first 16, 24 bits are randomized, but then the last they're random addresses. The thing ASLR does not randomize is the last 12 bits. So you can always you can do some weird offset math with that if you know everything's within like the same page or the OX 1000. So the question is, how do we jump to an address when every time we run the program it's random and it keeps changing? So there's kind of some initial bypasses that we can think of. With NX, we can't write our own executable code, so let's just jump to code that exists. So we can either jump somewhere in our program itself if there's something interesting we want to go to, or every program usually includes the standard library, and there's a lot of cool code, such as a function called syscall, which allows you to set up all of your parameters and then just do a syscall, and you don't even have to like write shellcode for it. Or from there, we have to deal with the canary. And so we need to figure out some way to read values off of the stack, because if the canary is on the stack, if we're able to, leak that information and use it the next time we overwrite to the stack, then we could just preserve the canary and the program knows no difference. And then for things like ASLR and pi, we need leaks to regions of memory that we're interested in. So for every region of memory that's randomized separately, right? So when I say randomized separately, the heap, the stack, your program are all placed at 3 different locations randomly. When I say the program, you can expect that the globals, constants, executable code are all contiguous. So you get something called the base address of everything. You can suspect that everything that you're going to interact with your program is all contiguous, but that entire block is randomly placed throughout your program. But once you have the leak, you can compute from any leak that base address and some offset. And this is an equation, so usually how you're going to do this is you're going to compute the base by taking your leak and subtracting the offset that you know from relative inspection. Because when you view these binaries in like a decompiler, you're given relative addresses, so you can figure everything out from there. Okay, so exploit primitives. So we have some building blocks of an exploit. We usually need two things to make a viable exploit. We need an arbitrary read and an arbitrary write. These two things together allow us to kind of break everything in a program. Because if we're allowed to read anywhere or read something somewhere, then we can probably read an address off of the program memory. And the stack stores many addresses. It stores return addresses to libc, to your program. It might store addresses to the heap, so on. And with that, we gain information about our program. And with arbitrary write, then we can affect return addresses. We can control registers. We can do these things to get code execution, things that we want to do, break the program, and so on. So you're going to need these three things on like a modern program to get some viable exploit. So another dangerous function. Gets was bad. We had no bounds checking, and there's better functions like fgets and things like that, which ask for a number of bytes or just a plain read. But you might see that people call those functions with the wrong number of bytes, so you still get a buffer overflow. This is worse. This is much worse. So printf is print format, which is very nice because if you want to print variables in your code, it's really annoying to convert those to strings and then do this in a very C raw way. So printf allows you to provide these neat little specifiers, for example, %s, and you can provide then a string as second parameter, and when it prints it out, it will print it for you. And then so you'll get the whole string like hello Kevin, who's not here. I'm sad. There's other specifiers like %d, which will print out in signed integer decimal, and print out those strings. And you can chain these together and get longer strings and append in the order that you use them your additional parameters. And so printf is something called a variadict function. So in the definition of the function header, it has all the parameters that it expects, comma, ... And so this is how you define a variadict function, writing your own program. So it's able to take as many parameters as you want. I think we have a few more. SDF format specifiers, yada yada. So you're able to provide them as much as you want, but you have to understand that first parameter is the format string. It takes in the base string it's working with and all the format specifiers, and then starts looking down your arguments to work with. So if I just did printf name, and name is just a variable, with Kevin, it prints Kevin, but if I provided the string %s, I didn't give it an argument. So where is it getting that argument? So, we can use any parameter we want. %p is quite nice because it formats 8 bytes of our argument into a hexadecimal number and prints it out like that. So if I just did write %p with no argument, well, it's going to get that argument from somewhere because it doesn't know when it has or hasn't been provided parameters. So if we look at the stack, this is where the idea of past arguments are on the stack. So with a lot of functions, I mentioned last meeting, for most of your simple functions, your arguments are passed in registers. So they're never touching the stack. They're all passed in registers. The function calls pulls them down. With printf and the variadict function, because it doesn't know how many it's going to work with, it's expecting to find the parameters on the stack almost explicitly. So if I do printf %p and then some variable b, then these local variables that I've passed into printf are before the return address, and it's going to pull this variable off when it parses the string, and then it halts. But if I don't have that variable, then it's just gonna start leaking out local variables of the caller, and eventually, there's no limit to the number of specifiers you can provide. You'll end up actually leaking the save frame pointer and return addresses of the caller function. So printf can give us a lot of information if used unwisely. So I can chain a bunch of them and read off values of the stack. And to bring back a little ND in this, if the string SIGPwny is on the stack, then it's going to show up in reverse order bytewise. So that's a pretty powerful primitive to work with, because now we can read values off the stack. We can get that stack canary, and if we have an arbitrary write later, we can preserve the stack canary without causing the program to crash. So other forms of arbitrary read, we can provide, when we do %s and provide like a constant string, in coding, we don't think about too much. That string just exists there and it happens. In practice, that string gets moved to the global text section and is just a global variable that's never written to. And so it actually gets replaced with an address. And so nothing is stopping us from providing our own address, and then we're able to read, any arbitrary like memory location as a string. And interestingly enough, printf is very powerful in how it handles format specifiers. The manual page provides like a whole chain of flags and strings you can put together for just printing out one type of value. And so if you provide this $3 idea, it will then skip the first two parameters and give you the third one without having to go in order and having parameters. And of course, if I don't provide 3 values in my printf, it's going to just grab the third value off of the stack. So we're able to grab the third argument and so on, and then we can read any position off of the stack. So we can get a lot of different kinds of information with just printf. So we need to be a bit careful here of how we do things. So we have, f gets name and then printf name. We want to get a specific address off of our printf. So, we use these format specifiers to get an address from the input string we provided, and then print out that address instead. Right? So if I give you a 16-byte string, where in the first 8 bytes I have that format specifier, it's going to then grab the next 8 bytes to be the format that I'm using, or the address that I call. So as you can see here, I have this, %n $s, which tells us to grab a string. I use some underscores to padding to keep everything 8-byte aligned. And then I provided an address to read that string from, because that's all read sequentially off of the stack. If the pointer is, saved directly on the stack. So, we pad, and we're able to use the p specifier to get the address before we use s to verify that things work out as we expected. Because %s will dereference the pointer, whereas %p will just read off the bytes that we care about. So that gives us arbitrary read. So that's pretty nice, pretty useful. So what about arbitrary write? Can we write with a printing function? Unfortunately, we can. So there's the %n format specifier. Why they added this, I don't know. It's caused a whole host of issues. This guy will take the address that it corresponds to and write the number of bytes previously written to that address. So I have a string prior to the %n that's like 300 bytes long, and then it will write that many bytes to the address given. So there's a couple ways to mess with this. Number 0, but if I have 4 A's prior, then number equals 4. Of course, if I do %500p, no $, what this causes printf to do is pad out 500 bytes before printing it. So now I can get some pretty large numbers stored in that variable. So nothing is stopping me from printing out the size of the address, which is a lot. but writing different addresses into variables that I wasn't expecting to. So we've had 500 characters. So OX1 is preceded by 497 spaces. Things like that. So we have a pretty strong arbitrary right with printf. And so with that, one unsafe call, just providing the string directly as a variable rather than using %s and then the parameter, we pretty much get full control over the stack. So again, the testing strategy is the same. You're going to do 8 bytes of that format with necessary padding, and then do the address you want to write to. So in the same way, you want to make sure that your address is correct before actually printing to it, or writing to it. Also, it should be expected that %n expects to write to an integer. So by default, it's going to just write 4 bytes in the little endian. You can provide a size format specifier, because of course there's more flags to this horrible function, called h, and h will cause it to write half as many bytes, and double h causes it to write a quarter as many bytes. And so you're able to just do like 1 byte overwrites, which is very simple when you chain sequences of format specifiers together. You can write out a whole integer altogether. Any questions about printf? That was a lot of information and how it functions. If you're confused, unfortunately, one of the best resources is the man pages, but it does explicitly state everything going on. Okay. So that's printf in a nutshell. So that gives us, stack leaking abilities, stack writing abilities. What can we do with that? Well, there's ROP, which we'll talk about in Poem 3 later down the line. But for right now, I want to kind of go back to libc. Libc is kind of a program that's loaded at the same time as your program, which contains all the code, globals, constants for the standard library. So in the same way that you write your program, and you have all the features you need, libc does need to get loaded too if you ever call things like printf or execve wrappers, things like that. So libc has all this nice features to it, and of course we're going to abuse the hell out of it. So if we get a leak to an address at libc, we can do the same thing where we compute the base, and then if we ever have control over a return pointer, we can return to the executable section of libc, where there's a lot of interesting functions to use. Now, that's too much to think about. So there's this tool called OneGadget, which basically searches through libc and says, hey, if you return here, it will open a shell. Because there are some aspects of libc that say, I need to open a subprocess shell to do XYZ thing. And so OneGadget will look through libc, and it'll symbolically execute code paths that will pop a shell, provided that certain register constraints are met. So for this libc that I used, it required that RCX is null, and that the seventh bit of RSP is equal to 0. So some constraints are pretty easy, some are a lot harder to set up. It just depends what version of libc you're using and what code path you're able to return from. So if you get a leak to libc, you can return to a OneGadget, which is quite effective and simple for exploit development. And so now I kind of want to go through a demo of some Pwn strategy. If you want, at this moment, you're welcome to kind of tune me out and start working on challenges. We did set up the Pwn 2 category, but I wanted to take a moment to talk about kind of my strategy of approaching binary exploitation problems and how you would go about doing, the process finding exploits, computing offsets.
Need the screen share? Yeah, go to the website, SIGPwny.com.
Okay. Is it?
You might want to. Oh, wait, that's right.
Yeah, I'll do that. Okay, sorry about that. And then I will do, oh, how? We'll go as large as it will let me. Okay. So this was a challenge from the CTF that we were doing over the past weekend. So it gave us two files, which was this restaurant v2 and a libc executable. So when you're given a libc, you can expect that your exploit is going to be based off of returning to libc in some fashion. So usually one of the first things I do is, can I switch to a lapel?
Yeah.
Hold on, I'm switching mics.
Turn that on. I think you can also just use this as a stand too.
Okay, are we good? Works for me. Okay, so what we're gonna do is the first step is using a tool called either CTFmate or PWN I. CTFmate basically allows me to set up a binary and a libc and automatically run those two patch restaurant v2 this program to use the libc that I was provided, because otherwise it's going to use the libc that is installed on my system, which may not be the one installed on the host machine. So usually the first strategy for PWN is to run the program, and if this was like real malware, you would like run this in container VM. But you know, I trust the program. So we run the program. It asks for some input. It takes it. It says show me your ticket to pass. I don't know what that ticket is, and then it crashes. And so with that, you know, we don't know what's going on. So the next step is to open up in a decompiler. I prefer Binja. We talked about using Ghidra earlier. So if we open up, you know, restaurant v2, Binja will pop up here. Can I zoom in? Probably not. So I'll try to point out things as they come. So Binja allows me to view this in like a pseudo C. What we're able to tell from this is kind of like, without worrying too much about like really fine details of you know, what variables setting up, how it like goes through registers or stack, we can get an idea of some control flow here. Is unreadable. Hold on.
Wait, Sam, why is the resolution so low?
I don't know.
I think like the actual screen resolution is not good.
Okay.
And so it's like kind of complicated. Yeah, let's do that.
I'm sharing to Zoom, but viewing this through Zoom is kind of terrible. Truly the best setup. You want to work?
Oh yeah.
Perfect. Okay. And then let me hide video panel. Go this way. Okay. So we can see that at the start, it opens up urandom, which is just a file on the Linux kernel that is constantly generating random bytes. It'll try to open it, check to make sure that it didn't fail, and was able to read from it. and it loads it into this buffer variable. All right. And from there, it does this welcome to restaurant that we saw. It then gets 1,000 bytes from input and loads it into a global buffer. The reason I can tell is just of syntax highlighting. So this is located down in some global variable. So going back to main, reads it into a global buffer, and then checks to once it does that, it does printf. But as you can tell, it doesn't load like %s and then use the buffer. It's using the buffer directly. So we have a printf vulnerability within this binary. From there, it asks for a ticket. It takes in an input. Scanf just allows us to re-text input it and place it into an integer. We can see what this data is. It takes it in as %x, so it's taking like a hex value. And if it fails, it goes to permission denied. And that's about all we know about this binary right now. So I'm gonna try and get to this restaurant function. But for right now, what I'm gonna do is clear. I'm gonna make a solve script. So I'm gonna go into VS Code here. Why use like a real editor? We're gonna start by importing. We're gonna start by importing phone tools. And from here we can do some automation where we can load our process. We can load our process up and kind of start sending and receiving information from it. So we know that the first thing we send is a buffer of some size, and it has the printf vulnerability. So we want to just verify that we're able to read values off of the stack. So we'll do SIGPwny to kind of like parse out that first line, and then we'll send a bunch of like pointer values and just see what happens. So from here, I'm just going to do r.interactive, which just hands control back to me instead of the program. And we're able to try that. Restaurant V2 does not exist because I spelled it wrong like an idiot. So as we can see, the output when it does printf buffer has instead leaked a bunch of different values off of the stack. And so it's important to figure out which value is the value we care about, right? Because there's a lot of like parameters and pointers within the stack. One of these is that random integer we generated. So there's a couple ways to figure it out. We can either try to do static inspection through our decompiler. So if we went back to that main function, we can actually go down a level of abstraction and find where on the stack the buffer should be. So we know that it's the processor is going to offset local variables from the RBP, the base pointer of our stack frame. So we can see that this is immediately after the base pointer that it stores this buffer integer. But that isn't entirely clear where it is in runtime. So what we can do is instead of kind of just doing this guesswork, we can attach GDB to our process. So we can attach GDB, go back to our terminal, exit out of this because we don't care. You have to, I don't have tmux installed. I bricked my computer last night, and so now everything is broken. This is not ideal. Oh no. Okay. So last night I made a terrible error. Which was somehow I moved a linker. I copied a linker from one location to the next, and it bricked my computer. I'm not sure how it did this because it wasn't a symlink. I'm like pretty sure it wasn't a symlink. This should. Everything's broken in it. Oh God. Okay. This is not great. I did not plan for this in the sense that I did not plan for my computer to break. Okay. I think I'm gonna fall back and kind of go back to this guy. So I'm gonna just talk about exploit, in order here. So we can find through GDB where that random variable is stored, and I will tell you ahead of now, it is stored at the 9th position that we can get during code execution. So when we call send line to send our format vulnerability, then we're left with just the output of that one pointer. Now in this case it was an integer, so it was only 4 bytes, I believe. So I had to grab just the latter 4 bytes of it, which is what this Python splitting is doing. And that is our ticket. So then we send line to the ticket, and we're given the we're given the program. So if this is on restaurant v2 patched, it is, but I need to copy. Everything is so screwed up. Okay. And then this should just be libc dot. So okay, bearing with me. Thank you all. Okay, so with that, I can interject with the interactive here, and we can see that it provided the ticket, and now it's given us this menu. So now we're in the second phase of this challenge, right? In our second phase, we're able to ask for a cheeseburger, hamburger, or custom dinner. If I ask for, or I guess they misspelled it, the program authors, it's a chessburger. And it prints out that line and then immediately just exits. So clearly we'll look at what the custom dinner does, and it asks what do we want to eat. We try to type something, and it tells us wrong choice and then exits. So at this point we go back to our binja, or decompiler. From here we can look at that restaurant function that we're now accessing after our printf exploit. So here, this restaurant function handles the whole menu. The only interesting here is calling custom. From custom, we get this gets overwrite, and you might be a little confused why there's 2 gets and only one call to take input. This has to do with how the compiler loads external functions. The first one does nothing. The second one is the one that actually calls gets here, but it just looks like the same. So we get just print what do you want to eat, and then it gets overwrite. And so we mentioned from last meeting that gets is unsafe. We can overwrite the return address. So I would normally at this point I would go to GDB, but I've broken everything, so it's quite unfortunate. So what we can look at is kind of you work through the exploit to kind of figure out how you control registers and whatnot. And when you work through format strings, this will come up in different ways and whatnot. Eventually, I worked through kind of an execution chain where there was a position I could return to that provides me a leak, and then I'm able to restart the program because pi is off in this case. So I can return to the start of the program, and I'm able to deduce a 1 gadget, which I found through an offset. And when I run the whole exploit in order, then it gives me a pause because I need a pause. Goes to error active, and suddenly I have a shell. And so I was able to, break through the program, get a leak, do all these things internally. I would show more, but I've broken everything. I don't think I can, which is quite unfortunate from my end. But I really implore you guys to try and find out, work with GDB, work with Binja or Ghidra and whatnot, and ask me, because there's a lot of moving parts that goes on with Pwn, and it's really hard to kind of visualize what's going on without like banging your head across it 300 times for several hours, like I did over the summer for several hours. But that kind of runs up what I wanted to do for demo. It was a little way more scuffed than I would have liked, but it is what it is. I think I'm going to need to nuke my laptop after today. No, I am not installing Nix. Okay, some wrap up. Where did I put the clicker? Here. Next meetings this Thursday, we have lock picking, so come learn to pick locks. Physical security is fun, things like that. We have a bunch of lock picks we just ordered, and a bunch of new locks we just ordered. This Friday we have Cedar Creek, so come learn about their opportunities, internships, things like that. If you are looking for a job this summer, or if you're graduating, I don't think we have too many like available looking for opportunity seniors in this room at the moment. That's what's on tap for next week. Challenges. So last meeting's phone sequence, this should have just barely given you enough to finish 3 and 4. So we talked about shellcode and we talked about printf format vulnerabilities. So both of those challenges should be a little bit more approachable now. The execute challenge does automatically give you a stack leak, so use that as your return address. Thought we had more. We also put forward all of the format challenges that we have in our vault. So if you haven't worked through those yet, a lot of those are just messing with printf and seeing how you can break your programs. So that kind of wraps up the challenges. There's the meeting flag again if you need to handle it. So thank you all for coming. I wish that was a little less scuffed, but it is what it is.